And I want to talk about reconciliation in phylogenomics. Phylogenomics for me is more like a buzzword, a fancy word to describe evolutionary analysis that involves whole genomes or at least large portions of it. And when applied to this thing we call reconciliation, well, traditionally, we only reconcile single gene families. And why I call this phylogenomics reconciliation is in this the topic of this talk is that we want to consider many gene families. Okay, so the difference is single versus many, and that's where this phylogenomic buzzword comes from in the talk. The plan will be as follows. I will assume that no one has ever really dealt with reconciliation, or at least multi-gene family reconciliation, and discuss the basics of it, and along with a little bit of history that does not involve my own research, but at least will get you a broad overview of how this problem evolved. And then I will talk a bit more about my own research on the topic. So reconciling with segmental duplications and reconciling synthetic blocks. So as I said, I'll talk about the very basics. So here's a species tree. Okay, I assume we've all seen a gene species tree before. By the way, sorry, do you see on my screen, I see, you know, this big thing on top that's hiding the top of my screen. Is that visible to everyone?
We only see your slides.
So never mind what I said. Okay, something is obstructing my view, but if that's not a problem for you, fine. Okay, so that's a species tree. So we assume tree-like evolution, no hybridation or stuff like that. And I will focus on the history of a single gene that belonged to the super mammal. So what you can do is trace the evolution of that particular gene along the species tree, and you get something like that. The history of that gene with speciation events, which are usually the side circles, or duplication events. So duplications, they create a copy of a gene in the same genome, and speciations just transmit the gene into the two descending species. And we might have gene losses, which indicate that a gene has acquired enough mutations to stop being functional, for instance. So that's what can happen to a gene tree, to a gene. And I won't be talking about horizontal transfers or incomplete lineage shorting. It's just the good old speciation, duplication, and loss here. But the thing is that that's the history of only one gene. But of course, that super mammal on top had more than one gene. It had maybe 10,000, 20,000, I don't know. But what that means is that for each gene of that super mammal, there is a history. And yeah, that's a bit misleading because all the trees are the same, but in reality, they're not all the same. But my point is that according to the traditional models that treat each gene tree independently, well, they would say that there was one duplication event for that gene and one duplication event for that gene and so on. But you might argue that, well, all these duplication probably might have occurred at the same time. So you might say that, no, this was a single segmental duplication event. All those 5 genes got duplicated at the same time. Okay, this is the kind of question that I'm interested in. Instead of looking at the events on a single gene tree, try to look at all the gene trees together and find clusters of events, if you will. Okay, so that's what I call the big question. If you're given many gene trees, possibly all the gene trees that you can find with respect to a set of genomes, how do you identify the events that affect several genes from several gene trees? That includes segmental duplications, segmental losses, possibly segmental transfers. And one interesting case of that are whole genome duplications, followed by block deletions most of the time. Okay, so how can we use reconciliation to identify those? So in a nutshell, to cover the basics of reconciliation, what it does is it identifies duplication, speciation, and losses when you're given a gene tree in a species tree. So it's important to notice the difference that when I was talking here, I was given the gene tree and all the events that were on it, but these have to be predicted. The typical input in reconciliation is the gene tree with the only thing known being the genes at the leaves, and the species to which the genes belong. So small a means that this is a gene from the A species, small c means that this is a gene from the C species, and so on. And now we want to infer that duplication events, well, genes that have undergone a duplication event or speciation or losses. And how do we find this? The traditional way to do it is to use what we call the LCA mapping. So LCA stands for lowest common ancestor. And what we do is we first try to map each ancestral gene, the internal nodes, to the species they probably belong to. For the leaves, that's easy, that's given. Okay, these are at the leaves, we have genes of today, so we know to which species they belong to. And for the ancestors, we use the lowest common ancestor of the species present at the descendants. So for instance, we map this to the LCA of A and C because the species present under it are A and C. So this gets mapped to here and so on. All right, so this is a very useful tool in most reconciliation settings. And we use it to identify segmental duplications. It's actually instrumental, this LCA mapping. And there's a simple rule if you want to know under the LCA mapping whether an ancestral gene has undergone species duplication, a duplication. Well, you just check whether it maps to the same species as one of its children. So this node maps to E, one of its children maps to E, so duplication. And yeah, there's a formal explanation for that if you set up the model right. I'll just say intuitively why this node on top has to be a duplication is that speciations send the gene to the two descending species, and obviously here it did not do that. So it's probably a duplication. Okay, that's just an intuitive reasoning, but that's the idea. As for gene losses, I will also stay at the intuitive level and just say that when you have a duplication in the E species, well, you expect to find one copy, the left copy in A, B, and C, and the right copy in A, B, and C. That was not the case here, so we will infer a loss on the path to C and on the path to B here because they were not observed. So this is a very basic way to find losses. There's a formal way to define where you have to put losses, but I don't want to get into this. So that's reconciliation with one tree. So that's quite an old topic. It dates back from the end of the 70s. But I want to focus on the situation where we have more than one gene tree. And again, in practice, you might have 1,000 gene trees or even more, but let's just say that we have two to see the slight difference that happens. And so if you do the LCA mapping, this is what you get. Assuming I made no mistake, but that seems fine. Sometimes I make mistakes on tiny examples, ironically, but this seems fine. And if you do the reconciliation, this is what you get. Two duplications on top. And what you might hypothesize regarding what I said in the introduction is that maybe these two duplications are the same event. Maybe it was a duplication of a segment that copied these two genes from the root simultaneously. But for that to make any sense, that duplication must have occurred in either D or E, but not both. Okay. So if you want to hypothesize that these two events are one event, you have to remap this deduplication. You have to say that no, this gene, if it got duplicated at the same time as the other, well, probably it belonged to E. So when you remap this to E, now you can postulate that this was a single event. Okay, two genes from the same species that could have existed at the same time might be in the same duplication. Okay, and that's one of the main differences when we do multi-gene tree reconciliation. And depending on what you do, you get a different number of duplications and a different number of losses. And that's the whole problem. How do you play around with remapping genes to other species and devise an optimization criterion for that? But this is the general idea of multi-gene tree reconciliation. What is usually done is you start with the classical LCA mapping, and then you say, okay, I might need to remap some genes to other species. This will change the reconciliation, but yeah, you do this remapping, and after you've done the remapping, you find your segmental duplications. And how to do that is not always obvious, either in terms of how you model the problem and in terms of algorithms. And I want to focus on the models first. Okay, right. Before I get into more details on the models, I just want to establish a few basic rules on, this is supposed to be a forward arrow, on the what you might define as a valid mapping. So a map is what I did with the drawn arrows. It's when you map the gene tree nodes to the species tree nodes, indicating to which gene and to which species each gene belong to. And you have to infer this map before you infer the segmental duplication. So we will say that a map is valid if for the leaves, you map for each leaf U, you map U to the known species that you're given for you, and you're time consistent. And here it just means that if you decide to map U, well, the species to which it is mapped has to be a descendant, not necessarily strict, but it has to be a descendant of where you mapped its parent. Okay, and that's a pretty basic rule. It just means that you don't want to map U to that species and its parent to that species, which makes no sense unless you are in some strange setting. Okay, so that's all we require on our gene tree, species tree maps. And in classical reconciliation, we say that a node of the gene tree is a duplication if either, as I mentioned earlier, U is mapped to the same node as one of its children, or if U is mapped to something else than the LCA mapping. So when you start with the LCA mapping and you remap something above, that becomes a duplication. Okay, and again, there are reasons for this. You can show formally that this is what must happen in most current models, but I don't want to go over this now. Okay, these we can take these as axioms. And a word on gene losses. Okay, all this is saying is that let's say you have U and its parent, and U is mapped here and its parent is mapped here in the species tree. All this is saying essentially is that if you have 3 nodes on the path, you will have to infer 3 losses because you have, if this is your mapping, you are failing to observe copies in each of these descendants, which indicates losses. Okay, so that's reconciliation in a nutshell. And now I want to talk about a few models of segmental duplications, of reconciliation with segmental duplications. So in the literature, you can find 3 main models that have been studied, and they all differ on, when you have multiple gene trees and you have your gene species mapping and you have the locations of duplications, the models differ on what they define as a segmental duplication. Okay. Because you can define what you allow in a segmental duplication in all sorts of ways. And I'll discuss briefly 3 ways to do this. So the earliest model, to my knowledge, is that, okay, when you have many gene trees and duplication events, what you might decide to cluster in the same segmental duplication is all the genes that belong to a common species. So what that means, this is a very loose model. On this example, it would just say that all these duplications that are mapped to the F species, that's just one major event. Okay, and the reasoning behind that, obviously this can't be the case, or not always, but the reasoning is that if there's that many duplications in the F species, probably there was something special going on, like rapid duplications in succession. So we might as well treat all of these as a single event. Okay, that's the basic reasoning behind that model. So yeah, this example would have just 2 duplications, 2 segmental duplications, all the Fs and all the As. But one obvious question is that under this model, since you can remap the gene to species mapping, you could say, why not just map everything to the F species and say that you had just one major duplication event, and you could always say that your whole set of gene trees has undergone one event under this model. So yeah, that doesn't really make any sense. So there's a restriction on what you should be allowed to remap under this model. So one popular restriction is the following: if a node can be a speciation under the LCA mapping rule, it shall remain a speciation. That's one restriction. So what that means is, for instance, if you reconcile the left tree, this will be a speciation, transmits the gene to the E and C species, to the two descending species. But if you try to remap this node, or if you try to remap this node to an F, according to the rules, this will become a duplication, and they don't allow it in this model. Okay, so that's one way they restrict the possible remappings and make the problem interesting. So you cannot break speciations, but you can remap duplications as long as it does not break a speciation, such as this C that you remap to an F. Okay, you can already see an algorithmic problem here, I suppose, that the question is, you start with the LCA mapping, and how can you remap each ancestral gene so that you don't break any speciation and you minimize the number of species that have a duplication. Okay, yes, I had it on the slide. This is what I just said. You want to remap genes so that you don't break a speciation and minimize the number of species. So on this example, you could do something like that, and you would only get 1, 2, and 3 things that we would call segmental duplications. Right, so this is the episode. We call it the episode clustering because you cluster episodes into a single event. And this can be solved in polynomial time with this restriction, and also for other types of restriction that I won't discuss here. And I won't present the algorithm, but if I had to give the intuition of how that algorithm works, it's just that, when you have a duplication event, let's say that it has a speciation event in the above and below, to make it simple. Well, since you cannot break the speciations, this duplication has in the species tree a range to where you can remap it to. Okay, and the range is determined by where the speciation occurred and where this one occurred. And so each duplication has a specific range that you can remap to. So you could add all the ranges together of all the duplications. Let's say, I don't know, that this one has this range, and so on. So you get a bunch of possible ranges, and your goal becomes to remap every duplication within its range. So no, let me put it backwards. Your goal becomes to choose a minimum number of species that hit every range. And this is a set cover type problem, but with respect to ranges on a tree, right? And yeah, and that paper from Recom, they found a way to manipulate these ranges so that you could get a polynomial time algorithm, but I won't go into further details. It can be done. So the second model, and I'll be more brief on this one, it's called the gene duplication clustering. So the criticism of the previous model is that it's too loose. You can put all the duplications in the same species into a single event. So to make it less loose, we have this restriction that you can only put 2 genes from 2 distinct gene trees in the same duplication event, but without the restriction on the mapping. So what that means is, if this is your input, you might want to remap things like that, but you cannot put all the Fs into the same duplication. You can put these 2 together, these 2, maybe, okay, this is getting messy, but you get the idea. You can only, if you have K gene trees, all your duplications will have at most K members, 1 per gene tree at most. So this is the second model on how they defined another way to define segmental duplications. And under this model, the problem is NP hard and even W1 hard with respect to the number of segmental duplications. And the main difficulty here is to find out where to remap your genes initially. It's actually an interesting paper. Honestly, I don't like that model so much. It's too restrictive, but the paper is nice because they define this other sub problem, which is some type of, they call it the ball and trap game, where you have a tree and you make balls fall into the tree, and there's a okay, I can't obviously get into the details of that, but they invent a game which turns out to be kind of equivalent to that problem and is W1 hard. So I invite you to read it if you like game type problems that relate to phylogenies. But the model I spend the most time on is what we call the minimum episodes model, which is kind of an in-between. So the duplication events can affect genes in the same species, but your duplication events cannot contain a gene and one of its descendants together, which makes sense. Okay, if you have a segmental duplications, well, it won't include a gene and one of its descendants normally. So what that looks like is, let's say this is your mapping. Well, you can align all the duplications horizontally, and all of these are valid segmental duplications under that particular model, but this would not be valid, for instance. Okay. And for me, that makes the most sense. If you think in terms of whole genome duplications, for instance, this is what it would look like. Like you would have these thousands of gene trees with a huge, like horizontally aligned duplication on top. And let's say you have a second whole genome duplication, because that happens. Well, you'll have another huge horizontal duplication with the doubled number of members. Okay, so that's the model. And since I'll be talking about this one, I can define that as an algorithmic problem. So you're given the species tree and a bunch of gene trees, and you want to find a valid gene species mapping that minimizes the number of such types of duplications. So some known results on that is, if you have still this restriction that I mentioned earlier, never break a speciation, can be solved in polynomial time, okay, under various other restrictions. But if you have no restriction on what you can remap to and where, it had remained an open problem that we managed to solve. In terms of algorithms, so it's not written, but the open problem was whether it could be done in polynomial time. Okay. I will mention another variant of this problem. I won't discuss it. I'll leave that for the experts on the topic. But here, notice that the problem is formulated as being given the species tree. But if not, you could formulate a problem where you're just given the gene trees, and you have to infer the species tree and the gene to species maps that minimizes the number of segmental duplications. And if you're allowed to infer the species tree as part of the process, it can be solved in polynomial time. It's a bit of a surprise for me, but yeah, it can be done. It's also an interesting paper. They define this other game type problem that turns out to be a sort of equivalent. And it's a nice paper also because they define what the optimal solutions in terms of the species tree look like. They have a very characterizable structure. So yeah, this variant exists and has been solved. Okay, so these are the three models that I wanted to present, mostly for historical purposes, because to my knowledge, everybody is looking at this model now. I still think it's not perfect and that there is room for improvement on the models themselves. For instance, you might want to include genome information, adjacency, centennial information to decide what a segmental duplication might be, but this is, in my opinion, the best model we have so far. All right. So I want to talk a bit more on that, and I'll have to accelerate the pace. It's already 3:30 here in Canada, at least. Yeah, so this is the problem I'm looking at, and I will mention that one naive way to do it is you could brute force enumerate all the ways to remap your ancestral genes on the gene trees, and for each map, you compute the minimum number of ME duplications under this particular mapping. And I'm mentioning this because this is a sub problem, okay? Even if you're given a fixed mapping, M, how do you even minimize the number of segmental duplications under this model? Reminder, this model just says that what you can put together are genes that do not include, do not share ancestry. And it's actually an easy question, because the model says that, okay, these two can be part of the same segmental duplication, but these two as well, and these two, or it could be these four, okay? All of that is allowed. So how do you minimize the number of segmental dupes under that model? Well, it turns out to be easy. All you have to do is start from the, if you want to know how many duplications there were in the F species, you just start from the top duplications, put them together, and then the second level is together, and so on. So everything is aligned horizontally. It's not the only way to optimize that, but that's one way to do it. So if you want to know how many duplications you need for a given mapping, you first look at the duplications in the F species, restrict to that, you get a forest, and the height of this forest tells you how many segmental duplications you have in that species. So pretty easy. So you have to do the same in this example for the A species. So you have 3 in F, 1 in A, for a total of 4. So given a fixed mapping, this is easy. The challenge is to find the best mapping that will allow you to minimize that. But what this allows us to do is to find an alternate problem formulation. Instead of minimizing over some definition of segmental duplications, we just need to find a gene species mapping that minimizes the sum of duplication heights. Okay, where by that I mean the sum over the species of the duplications on that species. Okay. And this has actually become the definition of the problem. Okay, most papers that I read nowadays use that as the problem and not that, oh, it's far away. Okay, forget it. And not the previous one that I gave. Okay, but I did want to show where that formulation came from. Okay, because it's often forgotten. It really is a consequence of what is defined as a segmental duplication, this duplication height thing. Okay, and I won't go into the algorithmic or NP hardness details because I could, but I'll just give the intuition as to why this problem is difficult to find this remapping that minimizes duplication heights. It really is that, let's say that I'm not satisfied with this duplication being mapped to A. I'd like to cluster it with another duplication in H. Well, I have to say that no, this gene existed in H instead. But according to time consistency, this one has to be remapped to H, and this one also. But according to the rules of duplication, now this has to be a duplication, and this has to be a duplication. So the main challenge is that whenever you change something, remap a gene, this has the potential to create a whole chain of duplications above of it. And you have to be careful about what you remap and where to create chains of duplications that are well controlled. Yeah, that's the main intuition behind the difficulty, and the complexity of the algorithmic problem was open. And not too long ago, with Ricardo Dundee and Céline Scornavaca, we showed that it is an NP-hard problem. And there's a reduction from vertex cover. I don't really want to talk about the reduction itself. It's not too pretty. I did take the main figure of the reduction just to give an idea of what kind of reduction we're into. Like you start from a vertex cover instance and you generate this huge species tree and these huge gadgets in the gene trees, and these corresponds to vertices of the vertex cover instance, and these corresponds to edges. And what can I say? I can say that the main intuition of the hardness is that each edge corresponds to a set of duplications that you'd like to map to a common species so that you can cluster them together. But you have to choose to which species you remap these carefully, because your choice is going to impact the height of duplications that you will create above. And there's a way to show that your vertex cover instance had cover size k if and only if there exists a combination of choice for all the edge gadgets that has a height of duplications that's not too high. That's all I will say about the NP hardness reduction of this problem. And I'd rather move forward and say that another thing we prove in that paper is that problem is also NP hard, even if you have only one gene tree in the input. And that I can convey the intuition more easily, because we initially proved that it's NP hard if you have many gene trees. If you want to show that it's hard on one gene tree, you can just take all your gene trees and link them in a single gene tree, but you create a huge separation by many speciations. And that essentially amounts to reconciling each gene tree separately, as if what is above did not exist. Okay, so that was a lot easier to show. So even if we have a single gene tree under this model, the problem is NP hard. Another thing I want to talk about in this model is the incorporation of gene losses. Sure, the hardness is a result, but as I mentioned earlier, the models, in my opinion, need improvement. And this is a humble improvement, but at least it's a step in the right direction. And by that, I mean, instead of considering only duplications now, we try to improve the model by considering gene losses into the optimization criteria. Okay, so we propose this problem formulation where you have a duplication cost and a loss cost. Now you want to reconcile your gene trees such that you minimize delta times the sum of duplication heights plus lambda times the number of losses. Okay, so these count now. So you could have two scenarios, and depending on your cost of duplications and losses, you will prefer one over the other. Okay. So one easy result is that if your loss cost is higher than the duplication cost, it's straightforward to show that all you have to do is use the traditional LCA mapping. You just reconcile every gene tree independently and you get an optimal reconciliation. Okay, and it's unique if your loss cost is higher. But the more interesting case is when you have that, when the loss cost is smaller. It's NP hard because we showed that it's NP hard when this is equal to 0. It was the result from before. But we did get this type of FPT complexity algorithm where it's FPT in the ratio between the cost and D, where D is the sum of duplication heights in your optimal solution. Okay, and it's a reasonable algorithm when the gap is not too large. In a minute, if I can convey the intuition behind this FPT algorithm, it really is that it's a theme in this problem that when you remap something, you create problems. So for instance, if this is your situation, this is the species tree. If you try to remap this B to C, according to the rules of reconciliation, this will force you to infer a whole bunch of losses. And depending on this ratio, there's a limit to where it's worth it to remap. Like when you remap a gene, you might save a duplication because you can cluster it with other duplications. But if the number of losses created is too high, it's not worth it. So that gives us like a bit like the example, the kind of algorithm that I gave before. That gives us a range where you can possibly remap duplications for it to be worth it. And if the number of steps k that you want to remap to is too high, it's never worth it. This can be shown. So we exploited that to design an FPT algorithm where you take a node, a duplication, and you try to remap it to all the possible species where you can possibly remap it so that it's worth it. And there are that many ways to do it. And if your gene tree node is well chosen, you know that wherever you remap it to, it's going to increase your duplication count by 1. So you get this search tree with degree delta over lambda and depth at most D. And this is where we get that complexity from. I'm skipping over a lot of details. This well-chosen is the crucial part, but I won't discuss that. This is the main intuition. Okay, so to move on, we did implement that FPT algorithm, and we applied it on 2 data sets. And what we did was to apply it on a few thousand gene trees. And since the ratio was not too high, it could be done. And we looked at the species that had many duplications mapped to them. No, not many. We looked at species that had a huge segmental duplication. So the largest one was this one. This species here had the largest duplication. And this is to show what this kind of algorithm implementation can be used for. This location coincides with a whole genome duplication that was found using complicated Centini techniques in this famous Nature paper. So if they had been 20 years in the future, they could have just run our algorithm and they would have found it, but it's not always that obvious because some other node had huge segmental duplications. So what this can be used for is to hypothesize locations of segmental duplications on the species tree. We also ran some other experiments, but I'll go quickly over this. In a nutshell, another implementation for the same problem found 5 segmental duplications, whereas we found 4 with a large gap in the cost. And that duplication that the others found and that we did not was this one. And that might give us a clue or an indication that we should not, that this might not have occurred. This might not have been a segmental whole genome duplication. Maybe it was, maybe not. It just gives us some more hypotheses to work with. Okay, so these were the experiments. I have another part to this talk, but I'll go over it briefly. This is just the conclusion for that part, but it seems I've been talking forever now. But this is the conclusion for the part, but I'll spend 5 minutes on the other problem and try not more than that. But I will mention some algorithmic challenges with this model, that even if we ignore losses, we don't know if the problem is FPT and that D parameter, the number of segmental duplications. And we don't know with the losses if you try to ignore this ratio that we had in the complexity. And in terms of modeling, I'd like to model segmental duplications and segmental losses, because I failed to mention that the losses in our previous model were not segmental. Would like to model the problem if we incorporate HGT, gene transfers, and we'd like to incorporate the informations of conserved adjacencies and the syntenies. Okay, this remains to be done. I'm currently working on that, mainly with Selinska-Navaka, but we're struggling a bit to devise reasonable models. Okay, so as I mentioned, I have another part. I'll try, like I said, I'll try to go quickly over this. I just mentioned synthetic blocks, and I'd like to share maybe one attempt that we did to integrate synthetic blocks to infer segmental duplications. Okay, and the story is as follows. On a simple example, let's say you have a simple gene tree and a simple species tree. You do reconciliation. This will find a duplication here. But what we have to remind ourselves is that these at the least are genes from the same family, which I call the green family here. But they belong to genomes. So these genes, they have neighboring genes. So let's say we're lucky and all the neighboring genes are in the same family. What I mean by that is that the left genes are from the blue family and the right genes are all from the orange family. And this is what, this is what we call synthetic blocks. Okay, they're segments of genomes with preserved gene order across the species. When we have synthetic blocks, this is a nice indication that there were probably segmental events that occurred. And we want to use these synthetic blocks to do that. And one thing you might do is just give a label to these leaves, and the label corresponds to the name of the block, and each of these blocks belong to a given species. And you might as well forget about the genes at this point. You just have a bunch of blocks, and you want to reconcile blocks instead of genes. And if you do that, you will infer ancestral blocks and their locations on the species tree, and you will infer segmental duplications. Okay, this is an obvious segmental duplication because it gave rise to 2 blocks in the A species. Okay, so we studied what we call the centenary tree reconciliation problem, where you're given a species tree and not a gene tree, but a centenary tree, which tells us how the blocks have evolved in a tree-like manner. And you want to find an evolution of blocks with a minimum number of segmental events. And as in the previous example, if all the blocks at the leaves are identical, this is easy. This is the same as traditional reconciliation, but with real data, we ran into problems because centenic blocks can vary in content because of losses, but other events. So just to give you an intuition on how the problem changes is, let's say you have this, the green family is not present in this block. If you have to reconcile that, we can do as usual, say that there was a block speciation on top and this segmental duplication, but somewhere along the path, there was this loss of green. And that explains why you do not observe it here. Or maybe it got displaced to another place, who knows. But that's the problem. And when we tried to define centenary tree reconciliation more formally, we had to define a whole range of new possible events. So what we defined is that a centenic block is a string of characters, and each character represents a color or a gene family. And you have to find all these types of things. You have to find the blocks at the internal nodes, the strings, and you have to find to which species each ancestral block belong to, and you have to find block speciation events, block duplication events, which can copy a partial substring or a whole substring. You have to infer partial block losses and whole block losses. Okay, so the models become more involved when you start considering like centenic blocks. And this is one thing that we try to do. So I will finish with an example. Okay, I could talk about this forever, but I have to stop at some point. I'm looking at the time, and yeah. So just to convey what the intuition about what the problem is, I will work on a small example, but non-trivial, and see what happens. So I remove the colors. Now the numbers represent IDs of gene families. Okay. And yeah, this is our situation of blocks at the leaves. Okay, so they're not perfect, but they're similar enough to be in content to be considered as centenies. And what we would do first is maybe do the LCA mapping, say that this was an ancestral block that belonged to the D species and so on, and start inferring the ancestral blocks. This one is obvious because these 2 blocks are identical, and probably got transmitted by speciation into 2 descending species. But higher than that, we will infer a duplication because you see that this block transmitted a block to B1 on the left and to B2 on the right. So it's probably a duplication, but of a whole block. But in fact, not of the whole block, probably just of the block 256. So this is what I meant when I said that you could duplicate a block partially. And yeah, so this is the kind of thing that we have to infer. And here we would infer a loss in the whole block because it's not present in the A species. Like this is a duplication. So you would expect 2 copies in both A and B, but it's not in A. So there was a loss. And yeah, we would infer this block at the root level and some segmental losses to explain why 5.6 was present here, but not here, and so on. Okay, so I won't drag on forever with this example, but we devised a model for that, and we're asking if we could have algorithms to infer all of that. So experts on the field might notice that this is similar to many genome rearrangement problems on trees. For instance, the problem of inferring genomes at the ancestors and I don't know, inversions under the branches, that problem exists. So this is a similar problem. We want to infer maybe not whole genomes, but large blocks at the ancestors, and we want to infer like genome events on the branches. Okay, so it has this flavor. Okay, but I will mention that The complexity of that problem, even though I did not define it rigorously here, it can be done, but the complexity is unknown. What I believe is that if you're given the sequence at the root, it's feasible, but this is conjecturing. I'll skip over that and just say that we studied the set version where instead of having ordered blocks at the leaves, you have a set of genes, a set of gene families. And if your duplications can copy any subset and losses can remove any subset, the centenary tree reconciliation problem can be solved in the polynomial time with a pretty much standard dynamic programming algorithm. All right, so like I said, I could talk forever about this topic. The problem I wanted to share the most was this centenary tree problem, but I will mention in 30 seconds that this is just the tip of the iceberg, because when you start wondering where this centenary tree comes from, it's not a gene tree. It's a tree that describes the evolution of all the blocks. And a problem that occurs is that if you have a centenic blocks, you could say that the centenary tree is the tree of one arbitrary family. Like if, if all the families agree on the same evolution, it's kind of obvious that all the blocks evolved in the same tree. But if you start getting conflicts, like if the gene families in your blocks don't agree, what do you do? And we're currently facing that problem. You have to find some minimal way to correct your trees so that they become compatible, which relates to other well-known problems. But in practice, this is what we get. Okay, so I will conclude here. I did have a few slides. I will mention that we did a proof of concept experiments on the opioids families and showed that it could be applied to interesting gene families, but honestly, I don't have too much to say in terms of biological insight here. We just inferred some segmental duplications and losses on a particular family, and that just to show that it could be used. But I will conclude here and say that we're still facing a lot of modeling challenges. I did mention some of them. Another one that I won't reread all of that, but another one I could insist on is that the centenary tree reconciliation problem, to be complete, in my opinion, should integrate order changing rearrangements, because we observed that the centenic blocks are not always exactly identical in terms of how they order genes. But when we start doing that, it amounts to reconstructing ancestral genome with all types of possible events on the branches, and it becomes quite complicated. So we're trying to find compromises right now. If you read the abstract, you notice that in the abstract, I said that I would talk about the problem of simulating genomes that evolve under segmental duplications. And I obviously did not talk about that because I changed my mind and decided that I would talk about the history of the models of segmental duplications instead. So sorry about that if you were here for this, but I will mention that it's not even trivial to simulate genome evolution with segmental events, because you have to choose the length of your segmental duplications and losses. And to my knowledge, current models, they all choose a location and the length according to a geometric distribution. And we don't think that this is the most appropriate way to do it. Does not consider the diversity of possible events that could happen. There's a lot to say just in terms of simulating, and why we're interested in simulations is, well, we need something to test our algorithms with, right? But before that, we want the most realistic segmental event simulator that we can find. And maybe some people here know about these, but we did not find one that was satisfying to us. We're currently considering modifying the zombie software for those who know about that. And we have algorithmic challenges, if you like, algorithms like me. We still don't have a truly scalable algorithm for that minimum episode problem that I presented. If you read the paper on the centenary tree reconciliation, you'll find variants on which the complexity is still open. And we have this problem that I mentioned quickly at the end. When you have your centenic blocks, you have a whole bunch of gene trees and you hope that they fit into a common evolution, but when they don't, you face algorithmic challenges as well. Okay, so I spoke for a bit longer than I would have liked, so I will finish here and just say thank you to everybody. All right.